All right, so for conditional probability, it's the probability that one event happens given that another event has already known to have happened. And this is called conditional probability. So in this symbol, we're looking for the probability of B given that we know A has already occurred. So look at this example. If we know that a person owns a home, what's the probability that the person is a high school graduate? So the known information is that they own a home. So the probability of being a graduate given they own a home. So home ownership is the total. So 340. And then on top is how many of those were high school graduates. So that's 221. So 221 over 340 is 0.65. So the second question says, if we know that the person is a high school graduate. So this time, that's the known information. So the probability of owning a home, given that they're a high school graduate. So this time, high school graduate's the total. And the amount that were homeowners were 221. So 221 out of 310 is 0.71. So that's how we do conditional probabilities. We can use conditional probabilities to check for independence. So two events are independent if the occurrence of one event has no effect on the chance that the other event will happen. In other words, if we do a conditional probability, so the probability of A given B is equal to just the probability of A, that the events are independent. And if we were to reverse them, the same thing would be true. The probability of B given A, then probability of B would be true. So I'm going to use this example to show you. So the probability of being left-handed given that you're a male. So the given information is my total. So left-handed males is 3. So 3 out of 23. And then the probability of being left-handed. So this time we take the total left-handed out of our total. So 7 out of 50. And that's 0.14. So since these are not equal, the events male and left-handed are not independent. So if we know two events are independent, we can find the probability of both by just multiplying them together. So that's the first formula. The probability of A and B is the probability of A times the probability of B, only if A and B are independent events. So an example of independent events would be tossing a coin. The first toss is independent of the second toss. So I can just multiply the probability of getting heads on the first toss times the probability of getting tails on the second toss. I'm sorry, heads on the second toss. The second formula is the conditional probability formula. So we've been doing this already without this formula, but the formula does help. So the probability of B given A, you have to do the probability of both, so A and B, over the probability of the given information, so the probability of A. And we did that on the page before with the homeowner and graduate. So if we know that a person owns a home, that was the bottom number. Then the top number had to be high school graduate and homeowner. It couldn't just be high school graduate. So then the last formula is if A and B are not independent. So when we're trying to find A and B, we have to multiply the probability of A times the probability of B given A. So an example of that is on this next page. So this is about teenagers and their internet usage, and then of those who have a profile on a social networking site. So 93% are online. That means 7% are not online. Then of those that are online, 55% have a profile, Therefore, 45% do not. We find this one by doing 1 minus the 55. So then to answer this question, we're doing online and have posted a profile. So the probability of online and profile. So that is, the probability of being online is 0.93. The probability of having a profile, given that they're online, is 55. So we just multiply these together to get the probability of both. So I have a couple examples we're going to run through. If you want to pause the video and try it before I go through it, I'll wait just a couple of seconds before I start doing it. So in this problem, we have light media users, moderate media users, and heavy media users. And so their probabilities are 17, 62, and 21. From there, they describe their grade. So of the light media users, 74% describe their grades as good. So the bad would be 1 minus 74. So that would be 26. Of the moderates, the ones that described their grades as good were 68%. So bad would be 0.32. And then of the heavy, good was 52%, and the bad would have been 48%. So it's usually only going to give you one of those probabilities, and you have to find the second one by subtracting it from 1. So the question is, what percent of young people describe their grades as good? So there's 3 ways we can get good. So we can get good with the light, so this branch. We can get good with the moderate, this branch. Or we can get good with the heavy, this branch. So we need to add those 3 together. So 0.17 times 0.74, 0.62 times 0.68, and 0.21 times 0.52. And then we would just add them all together. So we get 0.656. All right, so then this next example, it says, what's the probability that a pitcher throws 9 perfect innings in a row, assuming the pitcher's performance in an inning is independent of his performance in another inning? So since it's independent, then I can just do the probability of throwing a perfect inning times the probability of throwing a perfect inning times the probability of throwing a perfect inning. And I'm going to keep going until I've done this 9 times. So essentially, I'm doing 0.4 to the 9th. So the probability of throwing a perfect game would be 0.0003. All right, so this next one, it says approximately 5% of normal pregnancies will receive a positive result. So since they're normal pregnancies and they're getting a positive, that means there's something, the test is saying something's wrong when actually there isn't. So that would be a false positive. So 5% of normal pregnancies get a false positive. Among 100 women with normal pregnancies, what's the probability that there will be at least 1 false positive? So, to find this, if we have at least 1, we could have 1 false positive out of 100. We could have 2 false positives out of 100. We could have 3 false positives out of 100, so on and so forth, until we have all 100 that are false positives. Now, if I found the probability of each one of these, it would take me a really long time. So it's actually easier to find the probability of no false positives first. So the probability of getting no false positives, that would be 0.95 for the first person, 0.95 for the second person, 0.95 for the third person, so on and so forth until I got to the 100th person. So it would be 0.95 to the 100th. So the probability that none of these women will have a false positive is 0.006. So if I subtract this from 1, I get the probability that at least one of the women will have a false positive. All right, so the next question, what's the probability that a randomly selected household with a landline also has a cell phone? So this is a conditional probability. The condition is a household with a landline. So we're looking for the probability of a cell phone given that you have a landline. So if we use our formula, that would be the probability of cell phone and landline over the probability of landline. So cell phone and landline would be 0.6. Just landline is 0.78. So 0.6 divided by 0.78 is 0.77. All right, so this is a question. We're going to make another tree diagram. So we have 3 age groups: 18 to 29, 30 to 49, and 50 and over. So of these internet users, 20% are in this age group, 45% are in this age group, and 28% are in this age group. So within each age group, they either visit video sharing sites or they don't. So we're going to say yes, they visit the sites, or no, they don't. So of the 18 to 29-year-olds, 70% visit the sites, so 30% do not. In the 30 to 49 age group, 51% visit the sites, 49% do not. In 50 and older, 26 visit the sites, and 74 do not. So the question says, do most internet users visit YouTube and similar sites? So we're saying, do they visit the video sharing sites? So we have 3 branches that say yes. This age group goes out to yes, this age group goes out to yes, and this age group goes out to yes. So I'm going to find each branch, 0.27 times 0.7 plus 0.45 times 0.51 plus 0.28 times 0.26. So if I add them up, I'm going to get the probability that internet users visit these sites. So about 49% of internet users visit video sharing websites. So the question was, do most visit? So the answer is no. The second question, what percent of adult internet users who visit video sharing sites are aged 18 to 29? So this is a conditional probability. It says what percent of adult internet users. So the probability of being aged 18 to 29, given that they visit video sharing sites. So the probability of being 18 to 29 and visiting video sharing sites over the probability of visiting video sharing sites. So we actually already calculated that probability up here. So the top number we get by multiplying out this branch. So 0.27 times 0.7 all over 0.4913. And that gives us 0.385. All right, last question. This one's about drug testing. In this problem, you either use drugs or you don't. And it says about 4% of prospective employees use drugs, therefore 96% do not. If you use drugs, you're either going to get a positive test or a negative test. If you don't use drugs, you're going to get positive or negative. So the positive, a false positive, would be that you don't use drugs, but you end up getting a positive test. So that's 0.05%. Therefore, a true negative would be 95% of the time. A false negative means you use drugs, but you end up getting a negative test. That happens 10%. So the positives, a true positive happens 90%. What percent of people who test positive actually use illegal drugs? Again, this is conditional. So the probability that you use drugs given you have a positive test. So the formula would be the probability of drugs and positive over the probability of being positive. So to find the positives, we would have to go out this branch and we would go out this branch. So that would be 0.04 times 0.9 plus 0.96, whoops, times 0.05. And that's going to be my denominator. And I get 0.084. The numerator is drugs and positive. So that would be just this portion. 0.04 times 0.9 is 0.036. So I would divide those numbers. So 0.429, 42% of those who test positive actually use drugs.